Hello, hello, and welcome back to our discussions on the linear IC voltage regulators. And we have discussed in our previous module protection circuits used in the linear IC regulators. And one of the protection circuit was thermal shutdown protection circuit. And now in this section, I'm going to introduce to you another type of protection circuit that is commonly used in modern linear IC regulators. And the name of that protection circuit is current limit circuit. And there are two types or variants of this current limit. One is called as constant current limiting, and one is called as voltage dependent current limiting, also referred to as fold back limiting. So we will discuss in this module the concept of current limiting, that is the first circuit, and we'll see how it protects the regulator IC in the event of excessive load current IL flowing through the load. And the fallback limiting, we'll see using the variable resistors how we can actually activate that circuit. Okay, so stay tuned for continuous and very engaging discussion on the current limit circuit with respect to linear IC voltage regulators. So what you see on your screen is the circuit diagram or a block diagram of basic current limiting circuit. So here is your input voltage. Here is your output voltage of the regulator. A load RL is connected through which the specified rated load current can flow, the maximum that can flow. And in the event that load current capacity is exceeded, your current limiting circuit will activate and reduce the output voltage and the load current both at the same time. So we have also seen in our previous model, there are three control loops inbuilt with the modern IC regulators. One is a voltage error amplifier, which is basically used to compare the two voltages to its input terminal, and it senses the output voltage with the help of this voltage divider and compare it with the reference voltage. Accordingly, it modulates the current through this pass transistor and controls the load current and subsequently the load voltage. Second loop we saw in the previous discussion was about the thermal shutdown circuitry. And now this is the third type, that is the current limit. So what is the modification in the regulator? We have placed a resistor here that is called as current sensing resistor. Whenever the current flows through this resistor, there is a voltage drop is generated. That voltage difference is sensed or fed to the current limiting circuitry, which will eventually sink all the current, excessive current that is being delivered to this transistor and subsequently to this pass transistor, and therefore the load current will be controlled. So to summarize, I would say the function of the current limiting circuitry is to prevent damage to your regulator IC when there is an overload placed on the output of the regulator. It means if you have a very low value of low impedance, there is a possibility that heavy load current can flow through it and that can damage to your IC. So without current limiting circuit, the regulator would source excessively high amount of load current and destroy the pass transistor, the power transistor inside the part, because your power transistor due to excessive heat cannot withstand that. To prevent this occurrence, the current limiting circuit will cut down the drive to this pass transistor. As I said, it will sink all the current coming from this end. The output voltage delivered by the voltage amplifier, it will take off all the current. Okay, and so that the maximum safe current level will not be exceeded. it will ensure that situation. Okay. Now, have a look at the detailed circuit diagram of how the constant current limit circuitry will work in the typical regulator IC. So in the yellow, you can see that's the circuit diagram or the block diagram or schematic of a linear IC voltage regulator. And in the orange, you have put up an extra circuitry to control the load current, and that is called as current limit circuitry. Now, we will see the working of this circuitry step by step. So before that, I would like to point out that the maximum current that a linear regulator can supply to the load is specified on the datasheet. So many regulator and including LDO, low dropout voltage regulator, specify only a single value of maximum load current. Okay. And that value is guaranteed for any input output voltage within the maximum ratings of that part. So you refer to the data sheet and you see the voltage inputs and outputs, and there will be a single value of maximum load current for that part. For example, if a specific regulator IC is guaranteed to source a load current of at least 250 milliampere without going into the current limiting. So you don't activate the current limiting as long as you operate the IC within the specified value of maximum load current, and you also save the power dissipation, extra power dissipation into the circuit. So if you operate that particular IC below 250 milliampere as an example, so you can source that value of current as long as your output is in the range of, let's say, 1.25 to 30 volt range, and the input voltage should be at least, let's say, 1 volt above the output you choose. So if you choose 1.25 volt output for delivering a current of 250 milliampere, your input would be 2.25 volt, just at least 1 volt greater than the output. So let us focus on explaining the working operation of this circuit. So this is a resistor called as sensing resistance. This load current passing through will be sensed by this resistor called as I sense, which will develop a voltage that is directly proportional to the current passing through it. So this voltage that is across it, this voltage differential will be level shifted and amplified by the differential amplifier. So you see, this is a differential amplifier that is receiving the voltage drop across these two resistors. Here in the bottom right, we have drawn the schematic of the differential amplifier using operational amplifier. We know that there are two inputs to it. There are resistors at the input side. There is a feedback resistor and one more resistor R. So if you make sure RF is equal to R and R1 is equal to R2, in that case, output of the differential amplifier is given by RF divided by R1 in bracket V2 minus V1. So RF by R1 is just a gain set by the passive components of the resistors. Okay, so this is that differential amplifier. So what happens, the voltage at the output of the differential amplifier is basically a ground reference signal that is proportional to the current flowing through it. So more the current, more is the drop developed, more is the drop developed, more is the difference between the voltages, and more is the output voltage. So if the current decreases, the voltage decreases. If the current increases, the voltage increases. Okay. Now this output voltage of the difference amplifier is basically called as load current signal, which is coming from the differential amplifier. This is further applied to the inverting input of the current limit error amplifier, while the non-inverting input of this amplifier is connected to the reference voltage, and the value of this reference voltage is equal to the voltage at the output of the differential amplifier. So this is an error amplifier. If both inputs voltages are same, output is 0. So so the value of this reference voltage is equal to the voltage at the output of this differential amplifier when the regulator is driving the maximum current at the when the regulator is driving the maximum current, that is at the current limiting point. So there is no current limit exceeded yet, and this amplifier is working properly, and there is the output, this reference voltage is equal to the voltage coming at the negative input. So now what we see here, as long as the load current is below the limit threshold, the output of the current error amplifier is high. So the logic 1 comes here, for example, and the voltage error amplifier right here in the bottom in yellow keeps the regulator in the constant voltage mode. So our regulator is working fine, and the output here is high, and regulator is maintaining its operation in a constant voltage mode. However, when the load current reaches the limit threshold, for example, you can see in the graph, you see the IL is below the I limit, so the output voltage is constant. However, when the current limit reaches the I limit, the output voltage falls down, and there is a regulator enters into constant load current mode. We'll see how. So when the load current reaches the limit threshold, the output of the current amplifier drops to low. The logic 0 comes here, and it starts sinking the current away from the output of the voltage error amplifier, and this puts the regulator in a constant current mode. So when this current limiting occurs, the regulator output voltage drop, as you can see from the graph, below its nominal value, which will be sensed by the voltage error amplifier as an under voltage condition. So obviously this loop, feedback loop, will get activated again. The voltage here will be sensed, and it will be sensed that the voltage, output voltage, has fallen down below its nominal value. So the voltage amplifier then will drive its output high in an attempt to raise the output voltage. But the current amplifier right here will sink all of the current coming from the voltage error amplifier. So like the thermal limiter circuit we've seen before, the current limiter overrides the voltage amplifier, voltage error amplifier, to prevent damage to the IC. So this is how the control loops is working for the constant current limiting and the constant voltage amplifier. So again, when the load current will be taken back before the I limit value, voltage amplifier will be operated, and it will drive this more current into the power transistor, and the IL will be made constant, and subsequently your voltage will be made constant. So hope you understood this working principle of the constant current limit circuit, and this is an essential part addition to the modern day circuits. So stay tuned for more informative content like this.